I want to refresh your mind with this. So we would say, suppose that we have function g mapping A to a set B, and as we had mentioned before, this set here is called the domain, and B is called the codomain. So for the function to be to have an inverse, we would say that this function g would have to be 1 to 1, right? So 1 to 1. That would mean that a function g excuse me. This, in short, would be written that in the following way: if g of x1 is not equal to g of x2, if the function evaluated two values, if those evaluations are not equal, that's if and only if x1 is not equal to x2. So that's a way of saying that this happens for every value x1 and x2 that's part of the domain of the function. And if that is the case, then that function would have that property, sometimes called injective, right? Also, so the other property required for the invertibility of functions is being surjective. Okay, so we would say that a function is onto. Okay, so we would say that g is onto if and only if for every y in the codomain there exists a unique x in the domain, such that g of x equals y. So what I'm saying here in symbols is that for every member of the codomain, there is a unique member of the domain such that that member of the domain is mapped under G to that arbitrary member of the codomain. Okay, so that's a property of being surjective or onto. So a function has an inverse. Yeah, this is sometimes simpler with the horizontal graph test. Let me repeat it, okay? And before I then repeat it and do a graph before I write the inverse. So being surjective or being onto means that, remember, we are saying that G maps A into B. So A is the domain of G. So we're going to say, okay, now choose an arbitrary member of B. Choose an element of that set, the codomain. And then, if this function has this property, you will find out that that member of the codomain has, and also remember the diagram I did before. There was an arrow going into a box where G is, and then there is an arrow coming out, right? So here comes X, and here is the evaluation. That's the output, right? G of X lives in the codomain, it lives in B. So this says for every member of the codomain, there is that flip E means there is. And then that exclamation mark means unique. There is a unique X in the domain. Such that, and this also backwards, so I'm throwing a lot of symbols there, So this here means such that. Okay? For every member of the codomain, there is a unique member of the domain such that the function evaluated at the domain value is exactly equal to that arbitrary member of the codomain. Unique. Like here, the key is unique. So there's something about if you have the graph of the function, right? Consider two functions. Say, consider a function like this, and now consider a function like that. So graphically, this thing about being onto or surjective is that if you draw a horizontal line, okay, the y values are in the, I didn't draw the axis here kind of on purpose, but I hope that you're following me. The horizon, the vertical values, right? The codomain here are in the vertical axis, right? So B here would be part of the vertical axis. We're looking at pairs. So what we're saying is that whatever these values, the y coordinates that make this curve, those are values in, I like kind of pushing the boundaries of this. So the vertical values of this thing are the values that live on the codomain, all right? So you draw a horizontal line, and then you look at the intersections between that horizontal line and the graph. And that tells you that this is the one value y bar, for example, the y bar that lives in B. This will be an example as to when you draw the horizontal line and you trace back to the x values of the domain, then you're going to find that there are actually two values. I don't know, x1 bar and x2 bar. Two values that evaluated into that formula or that function give you the same value. This is not onto. This is not, this here is not onto. Because you draw the horizontal, and then when you try to go from the vertical axis to the y-axis, to the domain, you end up with more than one. That is still a function. However, is not a surjective function or an onto. Now, the other sketch that I did here, that would pass that test. Because if I draw a horizontal line, right, and I look at, this is some value y bar, and I try to map that back into the domain, I find that there is only one value into the domain which is matched with that value, right? So this is sometimes referred to as the horizontal line test for determining if the graph of a function tells you that the function is onto or not. Now, what I want to say is that if the function is both onto and one-to-one, if G is onto and one-to-one, then the inverse of G exists. So we're going to say that that function is invertible if it is both one-to-one and onto. And so why am I bringing this up? Well, I'm bringing this up because the inverse function G, like that, G to the minus 1, is defined is defined by G inverse of B being equal to A, if and only if G of A is equal to B. you could think of this in the following way. So if you have the function evaluated at a, and that is a value of b, then what happens if that function is invertible and you evaluate this at g inverse in both sides of this equation, then here on the left hand side you have the inverse evaluated at the function that leaves a, and you have on the right hand side g inverse of b. Think about taking the square root of the square of something, or taking the logarithm of the exponential of something, or the exponential of the logarithm. So that's kind of the formal way of writing how the inverse function cancel one another. Now, one of the theorems that we have from calculus is a theorem that involves inverse functions. So there is a theorem that we could state as follows. Suppose that we have a function mapping a to b, okay, and suppose that suppose the first derivative exists, and that first derivative is different from 0 for every value of the domain of this function. Now, let's call a to be the inverse under g of b, or let's say the g of a is equal to b. Remember, that's same as saying if and only if g of a is equal to b. Then, and this is the juicy part, the derivative of g inverse with respect to x evaluated at x equals b, the derivative of the inverse of the function evaluated at this point b, that would be 1 over the derivative of the function evaluated at this other value of x. Sometimes the notation may be a little too distracting, but it shouldn't be. So this involves the derivative of the inverse of a function. That function has to be onto and 1-to-1. And it involves the derivative of the original function. And somehow is relating that the derivative of the inverse function is in fact the reciprocal of the derivative of the original function. Okay, so on the left hand side we have the derivative operator acting on g inverse. On the right hand side we have the derivative of g, but it appears as a denominator. 1 over that expression is in the denominator. So let me show you a simpler version of such scenario. So if, in other words, an application of this theorem, if we are saying that y is a function of x, then the derivative of y with respect to x is 1 over the derivative of x with respect to y. I hope your head is spinning right now, because you could say, that makes sense. If dx and dy were two numbers that you could just think of dx, dy as a fraction and dy, dx as a fraction. They're not fractions. They're derivatives, which are limits, rates of change. There are certain limits. But this is an application of that previous theorem. Is an application that is useful in the following context. Useful in the following context. So suppose suppose y prime equals f of y. In other words, we're going to say here, suppose that dy dx is some expression of y. Then we have dy dx equals f of y. What happens if we, well, we can cross multiply, right? So let's say 1 over f of y is equal to 1 over dy dx. All I'm doing there is like cross multiplying. The f of y is on the right hand side. Well, I'm calling cross multiplying, but you can also think of multiplying by the multiplicative inverse or something like that, right? So we can convert that into 1 over f equal to 1 over dy dx, and this right hand side, because of what we discussed before, right? This right hand side becomes dx dy. So, in other words, we have that dx dy equals 1 over f of y, and we can take the integral on both sides, the integral operator here with respect to y. Okay, and doing so, this would imply that x of y is the integral. Let me go back here. The right hand side we had the integral of 1 over f. So x would be the integral of 1 over f dy.